Welcome to the Bean Pod, a podcast about decentralized finance and the Beanstalk protocol. I'm your host, Rex. Before we get started, we always want to remind everyone that on this podcast, we are very optimistic about decentralized finance in general and Beanstalk in particular. With that being said, 3 things. First, always do your own research before you invest in anything, especially what we talk about here on the show. Second, while you're doing that research, try to find as many well-developed, opposing viewpoints as possible to get the best overall picture. And third, never, ever invest money that you can't afford to lose or at least be without for a while. And with that, on with the show. One of the primary goals of Ethereum is scalability. Indeed, a world computer is only useful if it's able to manage and record an ever-growing number of transactions and computations. Now, earlier this month, the Ethereum network completed its much-anticipated transition from proof of work to proof of stake. Along with other benefits, the merge is promised to make the network more scalable by removing the congestion created by proof of work consensus mechanisms. But that's not to say that proof of stake has been the only scaling solution under development. Ethereum's Layer 2 blockchains offer scalable speed and capacity by performing transactions off Layer 1, then bundling and recording those transactions back in the mainnet. The underlying mechanisms of these L2 solutions, known as rollups, generally fall into 2 categories, optimistic and zero knowledge. To learn more about the latter, Mod, Publius, and I are spending this episode talking with Toghrul Maharramov, a senior researcher at Scroll. Scroll is a zkEVM-based rollup, and together we're going to discuss what that actually means and how this project can help make Ethereum faster and more robust without compromising security or transactional validity. Toghrul, thank you so much for joining us on the podcast.
Hello, thanks for having me on.
And a big welcome back to both Publius and Mod.
Thank you for having me.
Hey, Rex, thanks for having me as well.
Great to have both of you. So, Toghrul, how about you kick us off by kind of setting the stage around scaling and zero knowledge proofs?
Okay, so let's start with scaling first. So there's not really a clearly defined definition of what scaling is. People use different ways to describe what scaling is. What I would like to describe scaling as is a system which increases the throughput without increasing the hardware requirements. So essentially, because you could scale the system infinitely just by increasing the hardware requirements, but in that case, you just have less and less people who are capable of running the nodes. And the question is, how do you scale the system without increasing the hardware requirements? Because naturally, it sounds like the only thing you can do is just crank up the settings and process more transactions. And there are multiple ways to do it. So the original way to do it was sharding, which Ethereum first pursued from like 2016 or 2015. And that's when you split the blockchain essentially in into a bunch of chains that are run in parallel and just communicate with each other through the same protocol. In Ethereum's case, the security would have been shared because essentially the nodes who were running those shards were the same as the nodes who were running the main chain, but not all of them would run every single shard chain. Some would be allocated to different chains. But that has quite a lot of different problems in it because essentially because you split the committee sizes into smaller sizes, you get less security, etc. And it's also quite problematic to compose. And that's when off-chain scaling came in. So first it was Lightning Network and payment channels. Then we got Plasma, which was the original vision of how you would scale Ethereum via off-chain processing. But that had also a few issues. Specifically, it had a thing called mass exit problem. It's where you essentially attempt to exit the chain fraudulently without providing the data, so nobody can basically challenge you on what the exit is. And then the first zero knowledge rollup was born. So the paradox and the funny thing about zero knowledge rollups, they're not actually privacy preserving. They just use zero knowledge proofs. But essentially, if you take Scroll, Starknet, any other zero knowledge rollup, it's not actually privacy preserving. But the cool thing that the modern zero knowledge proofs have is something called is a property that we call succinctness. It's basically a property that allows you to verify the transaction in less amount of time that it would take to re-execute it, or a certain computation. It doesn't have to be a transaction, but in our case, it applies to transactions. So it makes sense to use zero knowledge proofs as a way to process transactions off chain, and then just put the zero knowledge proof on chain, and for the smart contract to verify it and say, oh yeah, great, everything is fine. And what was also interesting is that a few years ago, it was impossible to do that for something like EVM, because the computational overhead of doing that would have made the throughput negligible, like less than 1 TPS, even if it was technically possible. But thanks to a lot of breakthroughs that happened in the past few years, we're now at a stage where we have working systems live on Ethereum that allow us to process arbitrary transactions off-chain. And that's how we got here.
Zero knowledge proof specifically, what is the opportunity? You hinted at it there just a second ago, about that succinctness. Talk us through zero knowledge proofs and the opportunity that they provide.
So zero knowledge proof is a cryptographic system that allows you to prove that you can satisfy a certain function or an algorithm without actually revealing what data you use to satisfy it, or only revealing part of the data. So let's say you go to a supermarket and you buy some beer, and the cashier asks you for a proof that you're over 18. So if there was a centralized database that held all the IDs and all the information about the IDs, you can essentially prove with the zero knowledge proofs that you're over 18 without revealing who you are, or what your name is, etc., or your social security number, etc., etc. And the cool thing about them is they've been around for more than 40 years. I think the first paper a bit less. The first paper was published in 1983. And actually, two of the people who published it currently work in crypto. It's Sylvia Mickley, who works on Algorand, and Shafi Goldwasser, who's an advisor at Starkware. And basically, at first, it was an interactive system where basically let's say I was trying to prove something to you, and it was an interactive system when you would challenge me, and we would go back and forth until you were convinced. But then there came up a certain scheme that allowed you to transform an interactive proof into a non-interactive proof, where I could just prove it to you without you having to challenge me. It's called Fiat-Shamir transformation. And that's how non-interactive zero knowledge proofs started. And from there, they just kept improving and improving until we got to SNARKs. SNARKs stand for succinct non-interactive arguments of knowledge. So, and it doesn't really matter what the rest of the words mean. The only thing that matters in here is that they're non-interactive, so they don't really require you to interact with another person to prove that you're correct. And secondly, they're succinct, which what I already described. And you could theoretically use them to prove anything. So even an enormous amount of computation can be proven in a very small amount of time. So let's say a Planck proof takes a few milliseconds to verify, and that can prove literally gigabytes of processing and hours of processing. But obviously that would be very expensive to prove, so we use it on more viable things, and we applied the whole scheme to use it for processing transactions and proving the correctness of the fact that you proved that you executed the transaction correctly.
Yeah. So what you're saying is, to go back to your beer analogy, for the sake of zero knowledge proof, it's the same amount of, let's say, information that's provided outwardly to prove that I am over 18 as it would be to prove my entire financial history, despite the fact that, those two questions have very different answers in terms of the amount of actual information used to compile whatever that answer is. From an outward facing standpoint, it's yes, I'm over 18, or yes, I qualify for whatever, financial requirement there is. It's just that it's that very simple outward facing component.
So it depends on a concrete proof system. So there are some SNARKs and STARKs that are not constant. So the more computation it takes to prove, the more computation it takes to verify, but it's typically sublinear. So let's say if it takes 5 minutes to prove something versus a minute to prove something, it's not going to be 1 second versus 5 seconds. It's going to be more like 1 second versus 1.5 seconds. But some are near constant. So I don't think there's any proof system that is completely constant, because there are certain things that it'll depend on. But let's say if the number of public inputs, and by public inputs I mean the inputs into the functions that are not hidden. So essentially zero knowledge proof takes two types of inputs. One, which are public inputs, and those are the inputs that we share. So let's say you and I both know what they are. And then there are private inputs, the ones that I don't reveal to you. So you can use the public inputs to verify it, but you can't use my private inputs. Those are hidden. And in most of the SNARKs, for example, the systems that I described, the proof system that I described, the more inputs you have, public inputs you have, the more expensive the verifying is, but it's going to be negligible in terms of how much the difference. So you can consider it to be constant.
Gotcha. So let's transition more specifically to Scroll. So how does Scroll fit inside of this zero knowledge proof part of the scalability ecosystem?
So first of all, let me just describe what Scroll is, so people have a rough understanding. So Scroll is a zero knowledge rollup that uses a SNARK to prove the correctness of the execution that was done off chain, and Scroll is specifically zkEVM-based. And by zkEVM, I mean that our proof system can prove the computation that was done in EVM. So let's say you can take it's a bit modified, so we can't really prove the correctness of Ethereum transactions, but those modifications don't really affect the code, the smart contracts, and they are just efficiency improvements. So ideally, you could potentially just remove the modifications that we've done and prove the correctness of Ethereum's transactions with our system that we use. And so essentially what we do is you would send us a certain number of transactions, we would compute them, execute them, prove their correctness, and then commit them to Ethereum, which basically means that they're finalized without Ethereum having to re-execute all those transactions.
I see. So there's a lot of talk about bridges and other similar systems to help manage the relationship between L1 and L2. How does Scroll relate to systems like Optimism or some of the other bridges that are out there?
Firstly, it's a bit of a misconception that rollups. There's a lot of misconception about how rollups work, etc. But a rollup is essentially a sidechain that has a validating bridge that connects it to Ethereum. And what I mean by validating bridge, it's the bridge that verifies the correctness of the execution that was done by the sidechain. In our case, we use zero knowledge proofs, so it's explicit. You can only finalize a certain block if the execution was correct. In case of optimistic rollups, it's implicit, where you assume that in case nobody challenged the commitment within a certain period of time, that means that basically it is correct. And obviously, there are a few more nuances. So, for example, you couldn't just connect Solana to Ethereum and call Solana a rollup, because there are a few more properties that a rollup needs to have. So, for example, a rollup needs to inherit the censorship-resistant guarantees from the underlying base layer. So, in this case, Ethereum. So, let's say Solana, if Solana censors your transaction, you can't force the inclusion of your transaction through Ethereum, whereas in a rollup, you should be able to do that. So there are certain nuances that basically make rollups unique, but overall, the goal is to have a bridge between Ethereum and a rollup. Essentially, rollups are the most trust minimized way you can communicate between two different chains. And obviously, optimistic rollups have a bit of a different trust assumptions, but both of them are quite minimal. So in the case of an optimistic rollup, you just need one honest node that is capable of challenging the proof within 7 days, or depends on how you configure it. Whereas for us, you just need to trust that the zero knowledge proof system that you're using is secure.
So when I think about use cases, what are some specific use cases if I was looking to utilize Scroll, how would I implement it? Where would it be most useful? Walk us through a little bit of an opportunity there.
So I have an article coming about it, and basically there are rollups on Ethereum can be used for two different reasons. Either they extend the throughput of Ethereum. So let's say the demand, currently the demand for Ethereum is more than what it can supply in terms of block space. And secondly, it's to extend the features. So for example, something like StarkNet adds a new VM in a trust minimized way to Ethereum. So you can use Caro, which is a completely different system, to EVM, and you build different smart contracts there. We fall into the first category. So our goal is to extend Ethereum's throughput. We don't really add a lot of new features. We are looking into a few minor ones, but the idea is that from the user's perspective, the difference between using and developers as well. So from the users and developers' perspective, the difference between using Ethereum and Scroll is going to be unnoticeable. So in an ideal world, you would be interacting with Scroll and you wouldn't even know that you're interacting with Scroll rather than Ethereum. And so essentially we increase the throughput, but aside from that, Ethereum, because Ethereum is quite limited in terms of how much computational cycles it can provide. So essentially, I can't have a transaction, a smart contract that requires you to spend 10 million gas, because you would be paying thousands of dollars per transaction for it. Whereas on rollups, because it's done off chain, it should be relatively cheap. And so you could have different applications that weren't really possible to build on Ethereum because of the cost that it would take to use them. For example, something like an order book exchange, for example, you could potentially build it on Scroll and it will be quite cheap to interact with, whereas on Ethereum it would probably cost you like hundreds of dollars per transaction.
Gotcha. So I want to hand it over quickly and give Publius and Mod just a minute. I don't know if there was anything that you guys wanted to ask about or talk through. I still have a couple questions left, but want to hand it over to the two of you for a minute.
Yeah, I wanted to start with a question, Toghrul. From my understanding, from what you're saying, is that Scroll's objective is mostly scaling and not privacy. Is that correct?
Yep.
Yeah, and I see on your website you have that roadmap across different phases. Can you maybe take us through it and explain to us what each phase is for, or what do these phases mean?
So phase one is zkEVM proof of concept, and what that means is we have a minimal viable implementation of zkEVM that functions. So currently we can prove that a transaction was executed correctly, but we still can't prove all the opcodes. So there are some opcodes that are basically, you trust us that we can prove, but because we're in a testnet phase currently, it doesn't really matter. So it doesn't affect the security of your funds. And then phase 2 is going to be zkEVM testnet. So it's a fully fledged zkEVM implementation that can prove all the transactions and all the opcodes, and you don't have to trust us in any way. So you're essentially send the transaction off, we prove that it's correct, we put it on the testnet, and it's fine. And then phase 3 is proof outsourcing. So what we have come up with is that you could essentially scale the throughput of the product, increase the throughput of the protocol by just parallelizing the proofs. So what that means is, let's say you produce 10 blocks in a chain. Instead of computing the proofs sequentially, you can outsource the proof computation to 10 different nodes, or in our case, we call them rollers, to compute the proofs for them. And what it allows you to do is essentially, in the same time that it would take you to compute one validity proof, you can compute 10 proofs for 10 different blocks. And essentially, we have a system which would allow us to scale with the number of provers that we have in the network. And that's what it means by layer 2 proof outsourcing. And zkEVM testnet is essentially, once we have all the kinks and all the bugs sorted and the implementation audited and everything like that, will finally launch on the testnet, where you can use your real funds rather than imaginary testnet funds. And phase 5 is decentralized sequencer. So decentralized sequencer means that instead of a single entity building the blocks, you would have a permissionless system where anybody can be able to build blocks the same way you can in Ethereum. Just run the validator and you can build the blocks. But the problem with L2s and rollups specifically, it's quite complex to design a system which is decentralized, because you don't really want to introduce the overheads, because you're already paying Ethereum essentially for its consensus, and you don't want to just add another consensus on top of it. It's just a bit wasteful. So how do you decentralize the protocol without adding the consensus and keeping the overhead to the minimum? So it's currently in active research. We have some ideas, so it's not something that is impossible to solve. It's quite solvable. It's just the problem is that how we need to perfect it in a sense. We need to make it as efficient as possible before we launch it. So that will be the last phase of the current roadmap.
And right now you're on phase 2, correct?
So the phase 2 should be coming soon. So currently we have the zkEVM, and soon we're going to have the testnet fully functional, a public testnet.
And without adding any pressure, when do you think the phases will take long, or when will normal day-to-day users be able to use Scroll?
So you can. We currently have a pre-alpha testnet live, which basically is a permission testnet where you can sign up on our website, and we let people in batches to interact with it. So what you can do is, we forked Ethereum because we don't really want to cloak Ethereum, and basically you can interact, bridge between the fork of Ethereum and our rollup, and also we forked Uniswap, and you can use Uniswap and swap between the testnet tokens. But the full testnet, which will be public, meaning that you don't have to sign up anywhere or you don't have to ask our permission or anything, should be coming soon. I don't really want to commit to an exact date, because you know how dates work in crypto. If you commit to something, you're just guaranteed to have a postponement. So yeah, but it should be quite soon.
Publius, anything you want to jump in with? I even thought of a quick question as we were talking, but I want to want to give you the open mic for a second.
Appreciate it, Rex. Would love to ask you kind of what the difference between STARKs and SNARKs are, and why Scroll chose to use STARKs, and do they plan on using STARKs forever, or what is the 3 to 5 year plan for kind of where STARKs and SNARKs are going?
So the difference between SNARKs and STARKs was that basically it's in the STARKs name. So STARK stands for Scalable Transparent Arguments of Knowledge, and what they were is transparent. So with SNARKs originally, you had to have a trusted setup. What it meant is you had to have a certain cryptographic system where you would have like different computers participate together to compute the proving key and the verifier key, and what that means. But in that system, at least one of them had to be honest, so you had some trust. Whereas right now, there's some snarks don't need that anymore. So for example, the snark that we're using is Halo 2. It doesn't really need that. It's transparent. But we still refer to the snark as a snark because it's based on a snark that wasn't transparent, even though there is an argument for the fact that a transparent snark is a stark. So currently, there's not much difference between a lot of modern snarks and starks, but originally the difference was that starks didn't really have to have trusted setup.
Thank you. And kind of, I see in your roadmap here, kind of the vision, post mainnet is, as you mentioned, a decentralized sequencer and a more efficient EVM. When you say more efficient EVM, is that improving kind of, is that improving the actual runtime of the, the Stark, operations, or the SNARK operations itself? Or is that in actually, being able to, process the EVM, implement the opcodes in more efficient ways?
Both. So you could optimize the circuit and also the proof system you used. And also there are a few ways where you can optimize the execution time. So for example, we have been looking into, and also we're not the only one, like a few people are looking into it, is an approach to execution called optimistic concurrency, the parallelization. So what that means is you can basically execute multiple transactions in parallel optimistically and assume that they don't touch the same storage state slots. And if they do touch the same slots, you just revert to sequential execution the way it works now. And somebody called Brock, I think he works at Nansen, already did a proof of concept of that a year ago. And I think in his rudimentary test, he got a 5x improvement in terms of execution performance. So that's one of the things that could be improved outside the zero knowledge stuff. And also there are a few other things like the way the state storage works, statelessness, etc., that we're also looking into.
That's incredibly impressive. Really crazy to hear, kind of what's on the horizon.
For sure.
So you talked about having outsourced rollers a minute ago, and are there any concerns with working with outsourced rollers and when you talked about taking transactions and moving them from sequential to parallel, it sounds like there's some agreement risk in that. And do you have any concerns around that and how to manage them?
The only risk in execution parallelization is that you can potentially expose yourself to DDoS attacks when essentially a lot of transactions try to touch the same state without denoting that they're trying to touch the same state. So a similar thing to what happened in Solana a few months ago, where it went down because there was an NFT drop and a lot of transactions were trying to touch the same storage slot, and basically the nodes crashed because of it. Wasn't because of that, but it was the result of that. And that's the only concern. But you could You could mitigate that by by basically setting different prices on basically assume that, let's say, if you denote what slots you're going to touch inside the transaction, and then when you execute it turns out that you touch an additional slot, the cost of touching that additional slot in storage should be priced differently to what you price the slots that you actually denoted. And so we're thinking about basically pricing them in a way which disincentivizes attacks like that. So it can only happen because of uncertainty. So let's say if I'm interacting with a smart contract and I don't know what the outcome is going to be, so I don't know what slots it's going to end up touching. In that case, that's fine. It's only problematic if it's a targeted attack on a specific slot.
One more question. On the rollers, will they be able to be, trustless and kind of permissionlessly deployed?
Yeah, they will be permissionless.
That's incredible. Will there be any incentive to run a roller?
Yeah, so we're currently looking into a model similar to what Ethereum is going to deploy eventually, which is called proposer builder separation, where you have a relatively centralized set of nodes that have like quite expensive hardware that can compute and extract the maximum MEV they can from a batch of transactions, and then they bid. And essentially, what they do is they compete with one another by bidding to the leader of the round of the slot in Ethereum to be picked as the ones to be inserted into the block, into the consensus block. And so essentially that allows you as a proposer, the leader of the round, essentially of the slot, to collect MEV without actually MEV profits without actually extracting MEV. That work is done by the builder. So in this case, it will be similar. So a sequencers will extract the MEV, and then they will share the profits with the rollers. And also, obviously, transaction fees are the other part of the equation.
So kind of, when, this plan as we've described, before we decentralize the sequencer, but after we have kind of the rollers in existence, users will be submitting transactions to, kind of the sequencer entity, which will then basically say, I'm proposing these blocks. The rollers will kind of all compete to kind of win the bid in order to process that block, which will take some amount of time. And in the process, the proposer is, continually to build more blocks on top of that.
Oh, sorry. I was describing a scenario where both the sequencers and the rollers are both decentralized. So essentially, how it will work is you select, let's say, 5 sequencers per. Also, bear in mind it's an active research, so we might change the model completely by the time it's released. So let's say you select 5 sequencers per slot, and they compete by outbidding each other. And there's one roller who's responsible for picking the highest bid. And that's how it will work. In a centralized scenario, it's relatively easy. What we could do is something similar to what Optimism does, but Optimism doesn't have rollers, so they don't have to incentivize the rollers. So what they do is all the extracted MEV goes to public goods funding, because the sequencer is centralized and operating by them, and they don't really want to keep the profits from the MEV extracted. And what we could do is we could essentially give all the extracted MEV profits away to the rollers that are computing the validity proofs. And that would essentially act as an incentive prior to decentralization of the sequencers.
Awesome. So, I mean, in the case you just described, the sequencer, or you have kind of n rollers in one sequencer,
Yeah.
and then the sequence. Okay, awesome. But in the fully fledged model, will the rollers themselves kind of become the proposer, or is there still kind of 2 separate roles where there's like, a group of sequencers and a group of rollers?
In the second model, essentially, the sequencers will be the builders and the rollers will be the proposers. Yeah.
Thank you so much for, walking us through that. Really excited to, hear where further research goes on that end. This is all, incredibly insightful for all of us. So thank you so much.
No worries, of course. You're more than welcome.
So, two questions that kind of linger in my mind whenever we're talking to any project. The first is security concerns. It's something we can't get around right now. And so when you think about security concerns for Scroll, what goes through your mind? What are you and your team working on to manage right now?
The bridge, the main concern, I think, for any rollup is the bridge. And how do you minimize the probability of bugs happening on the smart contract level? And then if we're looking forward, like a few years forward, after, let's say, everything has been battle tested and we know that there are no obvious bugs in the system, how do you decentralize upgradability? Because especially for our project, obviously, if you choose to take a different path, you don't really have that issue. So let's say Fuel Labs, when they launched Fuel V1, they didn't have upgradability because they were like, yeah, if we launch a second version, we'll just deploy a new contract. But we can't really do that because our goal is to be EVM equivalent. So in case something changes in Ethereum, we need to be able to keep up with it, and therefore it has to be upgradable all the time. And how do you have an upgradable system that is also trustless and decentralized? That's probably long-term the biggest problem that we are looking into and we're trying to solve. Short-term, it's going to be the bridge, and I think what we're going to do, it's not really finalized yet, but I think the approach is going to be to limit the deposit. It's initially, so how the StarkNet works is every day they just increase the deposit limit by a certain amount, and that guarantees that in case something goes wrong, you don't lose 5 billion, but instead you lose a few million, which is a problem, but it's not a catastrophic problem, which can basically threaten the future of your entire project.
That's really insightful. And I mean, I feel like that is something we're hearing about so frequently right now, bridge exploits or bugs. And I think that's pretty insightful in terms of looking at that near term threat. The other thing that I love to ask about is the future, and you've already hinted at future capabilities. Anything else you want to cover in terms of what the project is looking at in terms of either capabilities or partnerships, new features, anything that comes to mind?
L3s, which are rollups deployed on top of rollups, because I think at this point it's clear that a single rollup is incapable of handling all the potential demand it might have. So we would need a way to scale out even more. And for a lot of applications, you don't really need composability. So let's say if you're building an NFT-based game, you don't really need that composability where you have to interact with different applications, etc. You can just be in your segregated system somewhere else, just infrequently interacting and bridging. So let's say if you need to add funds, etc. And for stuff like that, we're working on L3s and how to make L3s viable, because you can just deploy a rollup on top of a rollup. It's fine for some use cases, but for the majority of the use cases, you don't really need that level of security. So what you can have is a Validium, which is essentially a zero knowledge rollup that doesn't post the data on Ethereum, but instead uses some other data availability solution to store the data. So let's say you can use Celestia, or you can use something else to store the data, or you can have your own proprietary solution to store the data for your L3. And so, yeah, I think the future is going to be about L3s and how you make the deployment of them easy. So essentially, ideally, what we would like is that you can just, with a few clicks of a button, launch a new L3s, and you don't really have to deal with bootstrapping the sequencers, everything, and all those problems that you shouldn't really bother with as an application developer. You should just bother with your own application. And so we're working towards making it a reality. But that's a long-term thing. Let's get the scroll on the mainnet first before we start basically launching that.
Hey, nothing wrong with looking 3 steps down the road. That's really exciting. I mean, I feel like we're just getting to the point where we're having more and more conversations about L2s, be looking at L3s. That's I like that. That's the future.
Hey Rex, do you mind if I ask one more question here? So why are the Starks you use not privacy preserving?
It's not because they're not. They can be. They're zero knowledge. Oh, just one note. We removed the zero knowledge component of our proof system because it adds unnecessary overhead, and because we're not privacy preserving it, we don't really need that. But you can potentially return it back, and it's not going to be an issue. But the problem is, how do you do general purpose computation that is privacy preserving but simultaneously efficient? It's not really something that is quite common at the moment. So you could, so for example, Secret Network do it, but they use a trusted enclave, so in Intel SGX to do it, and we don't really want to do that. And also, because our goal is to be as similar to Ethereum as possible, Ethereum is not really privacy preserving, so we're not really concerned with that on an L2 level. On an L3 level, we might build some privacy preserving version of Scroll or something along those lines. But on an L2 level, our goal is to be just extension of Ethereum that allows users to transact and interact with Ethereum in a trust minimized way without paying an arm and a leg for a transaction.
I had one more question on my end. So Toghrul, you mentioned that on the testnet you have Uniswap as one of the supported maybe apps that you can work with, and I understand as well that other scaling solutions, they have certain apps that they support. Is this how it's going to be in the future, that whenever there is an app that needs to be, for example, supported or work through Scroll, that Scroll has to support that app, or will it be that anyone can, interact in the future with Scroll through any other app?
Yeah, it's a Uniswap fork, by the way. It's not a Uniswap. Essentially, no, you don't. It's a permissionless system. It's the same as Ethereum. You just have to pay the transaction fees to deploy on Scroll, and that's it. You don't really have to ask our permission or partner with us or go through us or even talk to us or know who we are. You just the same way as a developer on Ethereum, you don't really need to know who Vitalik is or what Ethereum is. You just need to press a button, deploy, and that's it. Your application is on Ethereum. So no, it's just right now because we don't want to overwhelm the current implementation that we have and also the servers that we built. We just want to take it step by step, where we firstly don't allow people to deploy their own contracts, just to see how the system works with our own contracts. And then once we make sure that everything is functioning as intended, we will open up the system so anybody is free to deploy their own contracts and do whatever they want.
So Toghrul, I want to turn it over to you. Is there anything else you'd like to share? Any closing thoughts? Anything we haven't covered that you want to talk through?
The only thing that I can add is that it's going back to the question that you asked previously, is I think that in the future, a lot of the user interactions and like a lot of our security concerns are not going to be focused on specific blockchains. So let's say Ethereum, Solana, etc. It's more going to be focused on the bridges. And so I think in the future, we will stop thinking in a way, oh yeah, it's Ethereum. We're going to be thinking in a way, oh, it's a Nomad bridge, or oh, it's a scroll bridge, or whatever. And yeah, it's just an interesting thought because I think at this point it's pretty clear that there's not a single chain that can facilitate all the demands of the users. And so essentially we are in a multi-chain future where multiple chains will exist in their parallel universes and have their own ecosystems, etc. And the main concern, because that's the thing that is the easiest to break, are going to be the bridges rather than the protocols themselves.
So I just going back to kind of the part where you said there's a function with private and public variables. Is it that the cost of storing and using private variables is way more expensive than having public variables? Or what? I'm just trying to conceptualize why the privacy is more expensive or more difficult.
But the private variables don't mean that it's actually private. It just means that essentially what you do is, well, let's say you execute the transaction and you have the public inputs into the, you compute the proof, and then you have public input. So you say the previous state, the hash of the transaction that you published, etc., that you executed. But all the steps that satisfy the correctness of execution of that transaction. So let's say at this point, after, I don't know, 3 steps, your stack was this, that. The protocol that is verifying it doesn't have to know about it. So it's basically just an additional overhead in terms of storage and latency that is not really necessary. So we hide it, but it doesn't mean that if you get the transaction, you can't recreate the same input. So it's not privacy preserving where you can't recreate something or extract the data from the original transaction. It's just we hide the intermediate state of the transaction because it's unnecessary for you to know it when you're verifying it.
Thank you so much for explaining that.
No worries.
Well, this is fantastic. Toghrul, thank you again for joining us.
Thanks for having me. It was fun.
Absolutely. And Maud and Publius, as always, thank you for your time too.
Thank you, Rex.
Thank you both. Everything that was said here today was incredibly insightful and, truly learned a lot. So thank you for taking the time to, come talk with us today.
You can learn more about Scroll on their website at scroll.io and find both the project and Toghrul on Twitter. The Bean Pod is a production of Beanstalk Farms, a decentralized autonomous organization. You can find us on Twitter, Instagram, Medium, Discord, and our home on the web at bean.money. You can also find me on Twitter at RexTheBean. And as a final reminder, this podcast is not financial advice. Thanks again for listening.